Okay, we're about to start our last topic for the block. So 6F is on reaction mechanisms. So some of this you will have seen in 108, but not all of it. So some new stuff. So the key idea is that a rate law of elementary reactions are commonly combined by making a variety of approximations or by identifying the rate determining step. And another thing you can do instead of making these two approximations is do a numerical integration, which is what you'll do on Mathematica in your lab on Thursday. So I want to think that when you think about a reaction, usually it doesn't just take place in one step. So usually a series of what we call elementary reactions. So for something like hydrogen reacting with Br2, it's probably just not a collision in one step and then the reaction takes place. So when we write our elementary reactions, each one has a molecularity. So if there's only one reactant, it's unimolecular, two bimolecular. Trimolecular is so rare that Atkins tells you not even to propose that in a mechanism. Three centers hitting together at the same time is just too rare. So the order of a reaction is an empirical quantity and is obtained by inspection of experimentally determined rate laws. So we learned how to do that earlier, how you take experiments, probably do initial rates, initial concentrations, and determine the orders. But the molecularity of a reaction refers to an individual elementary reaction that has been postulated as a step in a proposed mechanism. So you only can propose mechanisms and see if they're consistent. You never know for sure if that's the way the reaction happens. But a step in a mechanism has a molecularity because it's actually how the molecules have to interact with each other. So unimolecular, bimolecular looks like first and second order, but now because this would be a proposed step in a mechanism, it's a unimolecular step. This one with two is a bimolecular step. So when you think about putting together a mechanism, if you know something about the chemistry, that helps. So if this is our overall reaction, 2 NOs plus O2 goes to 2 NO2s. And if this is the experimental rate law, we can propose a mechanism that's consistent with that. So this mechanism proposes that two nitrogen monoxides have to collide and you form this intermediate. Then the intermediate could go backwards to form two molecules of NO, or it could go on to react to form 2 moles of the product. And so this shows you that the rate of formation of NO2 would be equal to 2 times Kb, the equilibrium constant for this guy, because we're talking about the rate of the product forming times O2. And the 2 is here because in this reaction, when it takes place, so when you have this times this and this reaction takes place, you get 2 moles of NO2. So there's a 2 there that says the rate of formation of NO2 is twice the rate at which this reaction takes place. So when you look at that, we're going to see in a little while that we want to get rid of that N2O2, and we'll work on that in a second. So we'll start out and talk about consecutive reactions, which the ones where the arrows really only go one way is a radioactive decay. So oftentimes something that's radioactive undergoes several decays at different rates to end up at a final product. There's another one that's a chemical one, but they oftentimes actually have a slight back reaction. So we're going to talk about the loss of A. A goes to I, and then I goes to P. So the loss of A is equal to I feel like something's missing on there. The loss of A equals the rate of formation of I. They're just saying of I, which equals Ka times A to make I in that step. And then in this step, the rate of loss of I is equal to the rate of formation of the product. So it equals Kb. So this would have a different rate constant times the concentration of I. And so A is changing in a first order reaction, if you notice up here. And so you can just, where it would have been natural log, now you can raise e to both sides and you can come up with this equation that relates the concentration of A to the concentration that you started with. And so the net rate of formation of I is equal to, goes up here, so it's positive, Ka times A, and then it goes down in the second step. So now if we take the concentration of A and we plug in how it changes because A changes in a first order reaction, you end up with a standard differential equation that says change in I with a change in time equals Ka times A minus Kb times I. And that's a standard differential equation. We're not going to look at the solution, but these are the solutions that would show you how the intermediate concentration changes with time and how the product does. And so we already have how A changes with time. So you can put all three of those on a graph and you can see it depends on the relative rate constants, but A just goes down, P goes up, and the intermediate comes in and goes out and usually has a maximum value in there. And if you look at the concentration of I and you take the derivative and set it equal to 0, you can find where that maximum intermediate would exist. And so that's the equation number 4, which you can then go ahead and do that self-test and then come back. So another type of reaction is when you have equilibrium taking place for some of the steps. So you may remember from Gen Chem, you did this one where if you have A plus B goes to some intermediate, then the equilibrium constant for that would be the intermediate over A times B. And if this is super fast and this is super slow, then the rate of the reaction can be described by the second reaction, but you don't want an I in here. So you can rearrange for I with the first equation and plug it in terms of K and AB, where they just replace this with Kb times the equilibrium constant. So it's actually easier to always think, just always work in molarity, and then you don't have to worry about how many standard state molarities you have, because that'll just be 1. So really the reaction rate constant is Kb times K, the equilibrium constant, because K times AB equals the concentration of that intermediate. So when you plug that in here, you get a rate constant times an equilibrium constant as your rate constant. And so that's a popular approximation to use to solve for an intermediate by assuming a fast pre-equilibrium. So you can go back and look at the N2O2 one we looked at, and you could do the exact same thing with that one. Assume that that first step is fast pre-equilibrium, and then you can go in and we had N2O2 in it. Whoops, that's the equilibrium for that one, sorry. We had, what did we have in there to start with? We had the rate of the reaction is NO squared times O2. And so that's from experiment. Oh, in here, so from our mechanism, its rate of the reaction is 2 times Kb times this intermediate times O2. So if you solve for that intermediate as a function of the pre-equilibrium, take the NOs over here, then you end up with an overall rate law that's rate constant times NO squared times O2. And that matches, right, the experimental rate law. It does. So another approximation that you probably didn't do in Gen Chem, unless maybe you took it somewhere else, which is called the steady state approximation. And the whole idea of the steady state approximation is if you have very short-lived intermediates, so maybe free radicals, intermediates that are very reactive and they're not going to last a long time. So if their concentration is very low throughout the reaction, then you can assume that the change in their concentration with the change in time is about 0. So if the concentration itself is small, the change can be set to about equal to 0. So I think I'm going to just do an example myself. They go back through this one where they use pre-equilibrium and now they use steady state, and you end up with a different rate law, which is important. Pre-equilibrium and steady state are different approximations. So I'm going to do self-test 6F.2, so that's on page 285. And it tells us that we have this reaction between A and B, and first it forms an unstable helix, and then that unstable helix can go on and form a stable double helix. And so we use the steady state approximation to derive the rate law. We start out and say the rate of formation of the product is a function of this second step. It equals Kb times the unstable helix. And then we're going to write every place that the unstable helix changes concentration. So it's created in the step where A and B react, so Ka times Ab. Reaction goes backwards, it's destroyed, so it goes down, negative Ka prime times the unstable helix. And then it also goes down in the second step, which I've given a Kb times the concentration of the unstable. So the steady state approximation is what I put on this line. It says, if that's a very unstable intermediate, its concentration never builds up. And so we can assume that the change in concentration is super small. We'll set it equal to 0. When we do that, then we can just rearrange this. Keep this on this side, take the two negatives to the other side. When you do that, you notice that it's 2 rate constants times the unstable. So I just pulled those out front times the unstable concentration. And then if I then solve for the unstable, I'm going to take these 2 rate constants over here, and I'll have that concentration because I want to plug that back in right there to get rid of an intermediate. So when I do that, I end up with the rate constant is a ratio of rate constants times AB. And so the steady state approximation is used a lot, and so is the pre-equilibrium. And what you're going to do in lab is see when those are valid, see how big the rate constants have to be in order to say something doesn't exist very long in the reaction, and you consider that its rate of change is equal to 0. Other thing we want to look at is this idea that Arrhenius equation tells us that the rate constant always increases with temperature, and that's not really true. And so if you look at this particular situation, this set of rate constants is your effective rate constant. So that's what you'd measure experimentally, but it's not a single rate constant. It's a ratio of rate constants. So if we go back to the Arrhenius equation, this would say that the rate constant is really equal to I'm not doing that one, sorry. I'm doing 7C, this guy right here, which is the one for the N2O 2 reaction. It just says that the experimental rate constant is 2 times Ka times Kb over the reverse rate constant for the first step. So it doesn't really matter what the reaction is, but this would be the effective rate constant. So will that always increase with temperature? If you plug in, so our K for a reaction is 2 times the Arrhenius equation for the rate constant for the forward reaction number 1. So it'd be AA, so the pre-exponential factor, e to the minus activation energy for the A reaction divided by RT, multiplied by KB, which is AB, e to the minus EAB over RT. And then in the denominator, you have another rate constant for a reverse reaction. And so if you pull things apart and look at it, pull out all the A's, they're not temperature dependent. They are, but we're not going to talk about that. They have a very small temperature dependence. It's really this right here that's going to determine our temperature dependence. So if we combine these exponents, we're going to add these. So it'll be negative, and then it'll be EA for A plus EA of B divided by, so we're going to subtract that guy, the EA of the reverse reaction. And so the overall activation energy is a sum of other activation energies. And that could be positive or negative, just really depends on, this guy could be much bigger than both of those. And so the EA overall could be positive or negative, which means your rate constant could increase or decrease with temperature. And it doesn't mean that you have a negative activation energy. It just means that the steps in the mechanism and how they relate to the overall rate constant ends up with a negative activation energy. The rate determining step. I think you've thought a lot about that probably in Orgo. And that simply is the step that has the highest activation barrier. Higher the activation barrier, the slower the rate, smaller the rate constant. So we've talked a lot about thermodynamics, but now when we're talking about kinetics, if you have two different reactions, and if you're far from equilibrium, the relative quantities of the two products is going to be related to the relative rates at which they're formed if you're under kinetic control. So that's when you're far from equilibrium. And so if you write product one, the rate of formation of product one is going to be this rate constant times AB. Rate of formation of product two is a rate constant for the second one times AB. And so if you look at that, you can determine that the relative concentration of the second product over the first is a ratio of the rate constants for those two reactions. So that's only true if you're far from equilibrium. So if a reaction is allowed to reach equilibrium, then the proportion of the products is determined by thermodynamics. So which one has the more negative Gibbs free energy rather than kinetic considerations. And the ratio of concentrations is controlled by looking at those Gibbs free energies for the reactants and products. And that is it. That is all of Chem 266, except for the labs and projects. We'll find something to keep us busy and